So what is our assumptions? So we assume initially a fail-noisy model. So processes may fail by crashing, and arbitrary network delays are initially allowed, but eventually the network stabilizes. So we have really a partially synchronous system or an eventually synchronous system, but of course we don't know what is the right period. And we assume for the moment a perfect point-to-point links. However, as you will see and consider by yourself, the algorithm works for weaker model where the network can drop messages and processes can crash and recover. But we will prove this algorithm only for the formal model, the partially synchronous system model. So what is the basic idea of the algorithms? So each process has a ballot, and ballots are unique. So each process owns a ballot, and the ballot will be a number n and a process identifier for each process. So this pair is always unique since the PID, the process identifier, is unique and it comes from a totally ordered set. And we are going to use the ballot, this pair, to rank processes. The process of the ballot that is highest will be the one that is elected. Then the other idea is max ballots is available to each correct process. And that happens because each correct process periodically gossips its ballot to all other processes. This gossiping process will make sure that every process has all the ballots of correct processes, and he can always select the max ballot. And processes are ranked. So eventually, every correct process will elect a process with the highest rank, and that is the one with the max ballot. And of course, if we have a good network connection, then every correct process will get the ballots of all correct processes, and he will select the one with the highest rank, and every other correct process will do the same, so they will agree on the process with the highest rank, and that is actually satisfies eventual agreement. So we are going to add what we call a majority requirement. What is a majority requirement? We will say that each correct process will only trust a leader if the leader's max ballot is among the collected ballots from a majority of processes. That's to say, when a process collects periodically ballots, if the leader's ballot is the max ballot, then he will continue to trust that leader. But sometimes we don't get the leader's ballot among the collected ballots. So what we do? So every process P that do not receive the leader's ballot, this is the leader's ballot, among the collected ballots, will consider that the leader has crashed. Might be correct or might be wrong, but he will do that anyway. And P will increase its ballot, so it will pump up its ballot to be higher than the leader's ballot by increasing the number n. Now, given that the ballots are increased monotonically, we satisfy the property of monotonically unique ballots, which the ballots are increasing and also they are unique. And the property of completeness, which says that each process will eventually trust, or in that case, elect a correct process, will always happen. Even if the leader fails, there will be always another process that comes and pumps its ballot up, and it will be eventually elected. So these give us these two properties. So this is a basic idea. So let us look now in detail to this algorithm. Step by step. So each process Pi is ranked, and the rank is, as I said, n and Pi. pidI, where n is an increasing epoch number, and pid is a process identifier. At any epoch n, under stable network conditions, the correct process with the highest pid will be the leader and remains the leader as long as he's supported by a majority. The requirement of majority, we are having it here so that we don't get leaders when there is only a minority surviving in the system for a while. And this is because anyway, the sequent Paxos will not make progress. So we just elect a leader if it is supported by a majority. Periodically, which means we have a timeout with a delay period, each process collects the ballots of correct processes in a variable called ballots here. And it also disseminates its known max ballot. So max ballot, as I said, will be disseminated among all processes periodically. So periodically again, on each time period, each process checks the ballots from a majority. And if the leader's ballot is absent, new election starts. And in this case, only connected majority participate in the new election round, and each process increases its own ballot to a value higher than this max ballot, and the one with a max rank will win the election in the next round, after that round. If a message from a suspected process is received, the delay is increased by delta. So we try to increase the delay. If we get an old message, it means that this guy actually was alive, but we couldn't receive some messages from him, so our period should be adjusted to be longer. So that will eventually satisfy the partially synchronous requirement. And of course, in real system, we adjust to parameters of what is allowed in that system, so we cannot just increase indefinitely. So here is the algorithm now, and you are going to get the code of this algorithm, the pseudocode. So we have a ballot leader election. We use a perfect point-to-point link, and everybody starts at round 0. Empty ballots, your own. You start with your ballot is your own identifier and 0, of course. You don't know the leader, and the max ballot is your own ballot. And the delay is delta, and you start a timeout. We are going now to check this in a nice way. We are going now to see what happens when timeout occurs. The first thing is this statement here. Forget it for a while now. Let's look to the rest, and we will come back to it. So you reset the collected ballot to 0, and you increase the round number, and you start a request response pattern here. So for all processes except yourself, you send a heartbeat to the process. This is your current round to identify the request reply pattern, and you disseminate what you know is the max ballot, and you start a delay. If somebody got the heartbeat request in round R with the max ballot, so it will update its max ballot here. This is updating the max ballot to the one that is highest, and then it will send the heartbeat reply with its own ballot. And when the requester receives a heartbeat reply, and if it is for this round, you add the ballot to the collected ballots. Now we are here collecting ballots. But if R is not equal to the current round, then it means we are getting an old message. To this guy, we did not really define our period correctly. So we adjust the delay. Now let us go back to this part here. And this says if we collected now a ballot from a majority, so it means the ballot I collected plus my ballot is greater than a majority, then we go and do check leader. Check leader will do two things. It will first see if the leader is among the ballots that we have here, so everything is fine. But if the leader is not among the ballots that we collected, then things are wrong. He might have been dead. And in this case, we try to bump up, increase up our ballot number. Now let us look to procedure check leader. So we have collected ballots now. So we pick up the max ballot among these collected ballots. When we do that, we get a top ballot and a top process. This is, we call it top. If the top ballot is not the max ballot, we know that the max ballot is the ballot of the leader, then we suspect the leader. And what we do, we increase our ballot number by increasing the epoch to a ballot that is higher than the ballot max. And we set the leader to unknown, which would mean we are really starting a new election process. If, on the other hand, the max ballot is equal or higher than the top ballot, then we execute this code. We check if the top is our leader, then we do nothing. But if the top is not our leader, so we update our ballot max. We say that the leader now is a top, and we trigger the leader to the higher process, which basically is saying now we have a new election. This is the top process, and this is the top ballot. You can see here each process gets a monotonically increasing ballot number with new leaders. So that is fine. And also you see is that when we did not detect the ballot of the leader here and we increase our ballot, in the next round we will get a new top. That's guaranteed. And so a leader election will actually then take 2 rounds. One when you pump up the ballots, and the next one when everybody detects that and elects the new leader. So now we have an algorithm that satisfies eventual agreement, since the period will increase so that heartbeats are delivered to each correct process by each correct process. The second is once a leader crashes or gets disconnected from a majority, this majority will increase its ballot to get a higher number than that of the leader. And in the next round, one of the processes in that majority will be elected based on the highest rank. And that will satisfy then eventual completeness, because eventual completeness says eventually every process trusts a leader. And of course, this ballot will be higher, so we have this monotonic ballot property. And if you think about it, the algorithm works even if messages are lost or processes crashes and recovers. And this is because we periodically do the gossip of the max ballot and our ballot numbers. So if a process is disconnected for a while or the message has been dropped, then he will catch up later. And that concludes the algorithm.